What if I told you that some Alaskan homesteaders are growing tomatoes and lettuce in greenhouses when it's 40 below outside, without burning a single drop of fuel or using any electricity? No propane heaters, no electric heat pumps, no wood stoves, just plants thriving in tropical warmth while the world outside tries to kill everything it touches. Here's the thing that breaks most people's brains about this. These aren't small hobby greenhouses tucked into some microclimate. We're talking about full-scale food production facilities running through the dead of an Alaskan winter when daylight shrinks to a few precious hours, and the air itself becomes a weapon against any living thing. The secret isn't about generating heat, it's about becoming an energy accountant for every single watt that nature provides. These homesteaders have figured out something that most gardeners never grasp. A greenhouse isn't a building, it's a thermal battery. And once you understand that shift, everything else starts to make sense. Most people look at a greenhouse and see glass walls holding in warm air. That's exactly backwards. What they're actually looking at is an energy collection and storage system that happens to include plants. Every design decision, from the buried tubes snaking under the floor to the black barrels lined against the south wall, is about managing one thing: the flow of thermal energy. Capture it during the day, hoard it at night, and never let a single BTU escape without doing its job first. The first thing you need to understand about growing food in Alaska is that a traditional greenhouse would be a death trap. Think about what you're actually trying to accomplish. You're building a thin-skinned glass box and expecting it to maintain tropical temperatures while surrounded by air that's actively trying to freeze everything inside it. A standard greenhouse works in mild climates because it only needs to hold a 20 or 30 degree temperature difference. Outside temperature of 40, inside temperature of 70, that's manageable with some basic solar gain and maybe a small backup heater. But when the outside air hits 40 below zero, you're asking that same fragile glass structure to maintain a 110 degree temperature differential. The math doesn't work, the physics doesn't work. The heating bill would bankrupt you in a week. Here's where it gets worse. Glass is an excellent conductor of heat. Every square foot of glazing is bleeding thermal energy into that hostile environment. The larger your greenhouse, the more surface area you're exposing to heat loss. Wind makes it worse, sucking warmth directly through any imperfect seals. Snow loading can collapse the structure. And if your heating system fails, everything inside dies within hours. Alaskan homesteaders learned this the hard way. The ones who survived figured out that the problem wasn't their heating systems. The problem was thinking they needed heating systems at all. Instead of fighting the environment with brute force energy, they started asking a different question. What if the greenhouse could heat itself? That shift in thinking changes everything. Instead of designing a building that needs constant energy input to survive, you design a thermal collection and storage system that happens to grow food. Instead of glass on all four sides, you expose only the south face to capture solar energy. Instead of fighting heat loss, you eliminate the surfaces that lose the most heat. Instead of generating heat, you harvest and store every available calorie from the environment. The physics is actually straightforward once you stop thinking like a conventional gardener. Solar energy hits the glazing and warms the interior air. That warm air needs somewhere to go, somewhere it can dump its heat for storage rather than just escaping through cracks and gaps. The soil beneath your feet is sitting at a constant temperature year-round, typically around 40 to 50 degrees just below the frost line. That's not freezing, that's not tropical, but it's not trying to kill your plants either. What these homesteaders discovered is that the Earth itself is the battery they were looking for. The climate battery is where the real magic happens. Picture this. During a sunny winter day, your greenhouse hits 80 degrees inside while it's 40 below outside. Most of that heat is going to escape through the glazing and kill your plants when the sun goes down. But what if you could capture that warm air and literally pump it into the ground, storing it like money in a thermal savings account? That's exactly what a climate battery does. It's a network of perforated tubes buried 4 to 6 feet deep in the soil beneath your greenhouse floor. When the interior air gets hot, a small solar-powered fan pulls that air down into the buried tubes. As the warm air travels through those underground pipes, it dumps its heat directly into the surrounding earth through basic conduction. Here's the part that most people miss. You're not just storing sensible heat, you're also capturing latent heat. That warm greenhouse air is humid, loaded with water vapor from plant transpiration and soil, evaporation. When that humid air cools down in the underground pipes, the water vapor condenses back into liquid. Every gram of water that condenses releases 540 calories of latent heat directly into the soil. That's massive free energy that most systems completely waste. The physics is beautiful in its simplicity. During the day, you're essentially charging your underground battery with both the sensible heat from the warm air and the latent heat from condensation. The soil acts like a thermal sponge, soaking up and storing that energy. At night, when the greenhouse starts to cool, that stored heat radiates back up from the earth, keeping your root zone warm and preventing the catastrophic temperature drops that kill plants. The ground temperature at 4 to 6 feet deep stays remarkably stable year-round, typically between 40 and 50 degrees Fahrenheit, even in Alaska. You're not trying to heat frozen soil, you're working with earth that's already above the critical threshold for plant survival. The climate battery just moves heat from where you have too much of it to where you desperately need it. Most systems run the air through 100 to 200 feet of buried tubing, depending on the greenhouse size. The tubes are usually 4 to 6 inches in diameter, with holes drilled every few feet to allow heat exchange with the soil. The fan only needs to run during peak heating hours, typically powered by a small solar panel that operates exactly when you have excess heat to store. What comes back up is cool, dry air that gets reheated by the sun, creating a continuous cycle. You're literally breathing heat into the earth during the day and having the earth breathe warmth back to your plants at night. It's a respiratory system for thermal energy, and it works whether you're there to manage it or not. The northern wall is where most greenhouses go to die. In a conventional greenhouse, that north-facing wall is nothing but glass, a massive thermal leak that bleeds heat directly into the coldest air around your structure. It receives virtually no direct sunlight during the winter months, which means it's all heat loss and zero heat gain. It's like leaving a door wide open to the Arctic. Alaskan homesteaders figured out that insulating the north wall isn't just important, it's more critical than the glazing itself. The south-facing glass captures solar energy. The north wall just hemorrhages it. So they stopped building north walls out of glass entirely. Instead, they earth shelter from that northern exposure. Picture this. Instead of fighting 40 below air temperature, you're insulating against 40 above ground temperature. That completely changes the thermal equation. 4 feet down, the soil stays at a relatively stable 40 to 50 degrees year-round. When you bury your north wall, or bank it with earth, you're no longer trying to maintain a 110-degree temperature difference. You're working with maybe a 30-degree difference. The technique is straightforward. Some builders literally excavate into a hillside, creating a greenhouse that's earth-sheltered on 3 sides with only the south face exposed. Others build a conventional foundation and then stack hay bales, earth bags, or bermed soil against the north wall. Either way, you're using the Earth's thermal mass as both insulation and a heat source. Here's what the physics looks like. An uninsulated north wall at 40 below is pulling heat out of your greenhouse at a rate that no reasonable heat source can match. But when that same wall is backed by 40-degree Earth, the heat loss drops dramatically. You're not eliminating heat transfer, you're just changing what your greenhouse is transferring heat to. Instead of feeding heat to the infinite cold of the atmosphere, you're feeding it to a finite mass of soil that actually holds and slowly releases that energy. The really smart builders take this further. They don't just bank earth against the north wall, they create thermal breaks and insulation layers. Rigid foam insulation between the wall and the earth prevents direct conduction while still capturing the moderating effect of the soil temperature. Some use double wall construction with insulated air gaps. What you end up with is a greenhouse that looks more like a bunker from the outside. The south face is glazed to capture solar gain. The north wall looks like it's growing out of the earth itself. It's not Instagram pretty, but it works when the temperature hits 40 below and your neighbor's conventional greenhouse turns into a frozen wasteland. This is fortress logic applied to agriculture. You don't build walls where the enemy can attack them. You build walls where the physics work in your favor. The north wall isn't architecture, it's a thermal strategy. Water is the ultimate thermal sponge, and that's exactly why you'll find those big black barrels lined up against the south wall of every serious cold climate greenhouse. While your earth battery handles long-term storage, these water barrels are your checking account for heat, absorbing energy fast during peak sun hours and releasing it back during those critical first few hours after sunset. Here's the physics that makes water irreplaceable. It takes 4.18 joules of energy to heat 1 gram of water by 1 degree Celsius. That's called specific heat capacity, and water's number is extraordinarily high. Compare that to concrete at 0.88 or steel at 0.46. Water can soak up nearly 5 times more heat per pound than most materials, which means those 55-gallon barrels become massive thermal reservoirs. Paint them black, and they transform into passive solar collectors. Black surfaces absorb roughly 95% of the solar radiation that hits them compared to maybe 20% for a white surface. During peak daylight hours, those barrels are drinking in sunlight and converting it directly to stored heat. A single 55-gallon barrel can store enough thermal energy to moderate greenhouse temperatures for hours after the sun disappears. But water isn't the only thermal mass at work. Smart builders integrate stone, brick, or concrete into their greenhouse floors and interior walls. These materials have lower specific heat than water, but they respond faster to temperature changes. Stone heats up quickly when the sun hits it and releases that heat quickly when temperatures drop. It's the perfect complement to water's slower, steadier thermal release. The strategy is a layered thermal response. Stone and masonry give you immediate heat release right after sunset, preventing that sharp temperature drop that shocks plants. The water barrels provide the steady, hours-long thermal release that carries you through the deep cold of night. Together, they create a buffer system that smooths out the extreme temperature swings that would otherwise kill everything in the greenhouse. Placement matters as much as materials. Those black barrels need direct southern exposure to collect solar energy, but they also need to radiate heat toward the growing beds at night. Some builders stack flat stones or bricks beneath growing benches where they'll absorb reflected light and ground-level heat. Others integrate thermal mass directly into the structure: concrete floors, stone retaining walls, brick heat sinks positioned to catch and release solar energy. The math on thermal mass is straightforward. More mass equals more stability. A greenhouse with 2,000 pounds of water and stone thermal mass will maintain more stable temperatures than one with 500 pounds. But there's a sweet spot where additional mass stops providing meaningful benefit and starts taking up valuable growing space. What you're building isn't just a growing environment, it's a thermal flywheel that uses the physical properties of matter to store energy when you have excess and release it when you're running short. The thermal mass doesn't generate heat, but it prevents the wild temperature swings that turn a greenhouse into a plant-killing freeze-thaw cycle every single day. The final piece of the puzzle isn't a technology at all, it's a heartbeat. Those chickens scratching around in the attached coop aren't just providing eggs and entertainment. They're walking, feathered furnaces running at 105 degrees Fahrenheit, 24 hours a day, 7 days a week. A 5-pound chicken generates roughly 35 to 40 BTUs of heat per hour through basic metabolism. That might not sound like much, but multiply it by a small flock of 10 to 15 birds, and you're looking at 400 to 600 BTUs per hour of continuous heat production. That's equivalent to a small electric heater, except it never turns off, never breaks down, and never needs fuel beyond the kitchen scraps and grain you're already feeding them. The integration is where the genius shows up. Instead of housing chickens in a separate building, these homesteaders attach the insulated coop directly to the greenhouse or build it into the earth-sheltered north wall. The body heat from the birds bleeds through shared walls or connects via small vents, providing just enough background warmth to keep the greenhouse's ambient temperature above the critical threshold where plants shut down and die. But the heat is only half the story. Every time those chickens exhale, they're feeding the plants. Carbon dioxide is essential for photosynthesis, and in a sealed winter greenhouse, CO2 can become the limiting factor that stops plant growth even when temperature and light are adequate. Commercial greenhouse operations spend serious money on CO2 enrichment systems. These homesteaders get it free from livestock respiration. The science is solid. Elevated CO2 levels up to about 1,000 to 1,500 parts per million can significantly boost photosynthesis rates in most food crops. Normal atmospheric CO2 runs around 400 parts per million. A small flock of chickens in an attached space can push greenhouse CO2 levels into that optimal enhancement zone without any mechanical systems or bottled gas. Some operations integrate rabbits instead of chickens or run both. Rabbits generate similar metabolic heat, produce excellent manure for composting, and their respiration contributes the same CO2 benefits. The key is sizing the livestock population to match the greenhouse thermal load without overheating the space during peak solar gain hours. The really sophisticated setups use the animal waste as another heat source. Fresh chicken or rabbit manure generates significant heat as it decomposes, sometimes reaching 140 to 160 degrees in an active compost pile. Managed properly, that decomposition heat can be captured and directed into the greenhouse thermal system while producing finished compost for the growing beds. What you end up with is a closed-loop biological system where every component serves multiple functions. The animals provide heat, CO2, fertility, and food production. Their waste becomes soil amendment and additional thermal energy. The greenhouse provides them with a moderated climate and protection from predators. Nothing is wasted. Every calorie, every breath, every gram of manure contributes to the overall system resilience. This isn't just animal husbandry, it's biological engineering that turns living creatures into infrastructure components. The chickens aren't just livestock, they're the greenhouse's life support system. The real breakthrough isn't any single component, it's understanding that you're not building a greenhouse at all. You're engineering a thermal ecosystem where every element feeds energy to every other element. The sun doesn't just heat air, it charges your earth battery, loads your thermal mass, and powers the fans that circulate warmth into storage. The soil doesn't just grow plants, it moderates temperature, stores solar energy, and provides the stable thermal foundation that makes everything else possible. Watch how the energy flows through a complete system. Morning sun hits the south-facing glazing and begins heating the interior air. That warming air rises to the peak, where intake vents pull it down into the climate battery tubes. As the hot air travels through buried pipes, it dumps both sensible heat and latent heat from condensation directly into the soil mass. The cooler, drier air returns to the greenhouse to be reheated, creating a continuous charging cycle. Meanwhile, solar radiation strikes those black water barrels and stone thermal mass, converting light directly into stored heat. The animals contribute their steady metabolic warmth and exhale CO2 that feeds accelerated plant growth. Their waste decomposes in managed compost systems that generate additional thermal energy while producing fertility for the growing beds. As evening approaches and solar input drops, the system reverses into discharge mode. The earth battery begins radiating stored heat back up through the soil. Water barrels and stone masses release their accumulated energy into the airspace. Animal body heat provides baseline thermal support. The decomposing manure continues generating warmth from biological processes that operate independently of solar input. What emerges is energy resilience through redundancy. If clouds block the sun for days, the earth battery still holds enough stored heat to prevent catastrophic temperature drops. If the thermal mass reaches capacity during peak solar gain, the excess heat charges the underground system. If the climate battery reaches saturation, the animals and compost systems provide backup heat generation. The symbiosis goes deeper than thermal management. Plant transpiration creates the humidity that gets captured as latent heat in the earth battery. Root zones warmed by the climate battery accelerate nutrient uptake and growth rates. Higher CO2 levels from animal respiration boost photosynthesis efficiency, which increases plant biomass and transpiration, which feeds more humidity back into the thermal storage cycle. This is why the system works when individual components fail. If a heating system breaks, you freeze. A thermal ecosystem adapts, redistributes energy, and maintains stability through integrated redundancy. The greenhouse isn't powered by the sun, It's powered by the intelligent arrangement of natural processes that capture, store, and exchange energy without requiring external inputs or mechanical reliability. This system succeeds precisely because it can't break down. There's no furnace to malfunction at 3 a.m. when it's 50 below. No electrical components are expected to fail during the ice storm that knocks out power for a week. No fuel deliveries that can't make it through when the roads close for days at a time. Look at what actually runs this operation. Gravity moves warm air into the Earth's battery tubes. Conduction transfers heat from the air to the soil. Thermal radiation releases stored energy from water and stone. These aren't technologies, they're physics. They operate according to the fundamental laws of thermodynamics, which don't have off switches or maintenance schedules. The only mechanical component is that small solar fan that helps circulate air through the climate battery system. Even if it fails, natural convection will still move some warm air into the underground tubes during peak heating hours. The system degrades gracefully rather than catastrophically. When your backup plan is the laws of physics, you don't worry about spare parts or service calls. This reveals something crucial about real resilience. The most robust systems aren't the ones with the most sophisticated technology, they're the ones that work with natural forces instead of against them. Every piece of high-tech equipment you add creates another failure point. Every fuel dependency creates another supply chain vulnerability. Every complex control system creates another thing that can break when you need it most. The thermal ecosystem approach flips that logic. Instead of overpowering the cold with brute force energy, it cooperates with the environment's existing energy flows. Instead of fighting heat loss, it eliminates the surfaces that lose heat. Instead of generating warmth, it captures and concentrates the warmth that's already available. The result is more reliable than any mechanical system because it's based on cooperation rather than domination. That's the deeper lesson here. When you design with physics instead of against it, you don't need to survive the cold. You can make it work for you. The Earth's thermal stability becomes your foundation. Solar gain becomes your power source. Thermal mass becomes your battery. Animal metabolism becomes your backup generator. The system is resilient not despite its simplicity, but because of it. This isn't just about growing food in impossible conditions, it's about understanding that the most powerful technologies often look like they're not technologies at all. When you design with physics instead of against it, you don't need to survive the cold, you can make it work for you. These Alaskan homesteaders have proven something that cuts against everything we're taught about modern agriculture. The solution to extreme conditions isn't more energy, more complexity, or more expensive equipment. It's intelligence applied to simple systems that can't fail because they're built on the fundamental laws of nature. That thermal ecosystem, the earth breathing heat through buried tubes, water storing sunlight in black barrels, chickens warming the air with their bodies, soil moderating temperature swings, operates every single day, whether you're there to manage it or not. It works during blizzards, power outages, and supply chain disruptions. It works when fuel prices spike and when delivery trucks can't make it through. It works because physics works. The real breakthrough isn't the individual techniques. It's the mindset shift from fighting the environment to partnering with it, from generating energy to harvesting energy, from complex systems that break to simple systems that adapt. That's what resilience actually looks like. Not the ability to overpower harsh conditions, but the wisdom to design with them instead of against them.